Hello everyone, I'm Laixin from Shanghai University. Today I would like to introduce our work towards better modeling with missing data, a contrastive learning-based visual analytic perspective. This is a joint work with Tencent Interactive Entertainment. We typically input a data set to train a machine learning model. In practice, some values in the data set might not be recorded and are represented as null. The data fed into the ML models is imputed to ensure there is no missing values. However, the imputed values are estimated by algorithms and differ from their original counterparts. Regardless of how robust the imputation algorithm may be, they inevitably introduce bias. To address this issue, we formulated the data missing problem as a subproblem of contrastive learning. For an incomplete sample, the ML models should learn the similarity between its complete counterpart and the dissimilarity between any other samples. As a result, the trained ML model could take the incomplete data to make predictions. Moreover, in order to enable ML practitioners familiar with contrastive learning to benefit from our system, we developed a visual analytic system series to support users in understanding, analyzing, and improving ML modeling of observed data with missing values. Our system comprises two parts, the backend engine and the front-end visualization. The backend engine is a contrastive learning framework that supports the usual steps for ML training. ML practitioners can model missing data without imputation. For each step of backend engine, the front-end visualization provides helpful interactions, especially for steps that significantly influence the performance of contrastive learning. This enables users with limited background knowledge of contrastive learning to leverage our system for measuring and diagnosing training data. Specifically, the architecture of our backend engine is the implementation of formulation mentioned above. Consequently, in the embedding space, the data point is tuned to be appropriate close to its positive pair and sufficiently distant from its negative collections. However, this training is a challenging task. For instance, anomalous training can result in a data point becoming identical to its positive pair, despite their different features and labels. Therefore, the front visualization is critical for CL performance. It helps the identification of the hard examples, which contributes to effective training. I will explain the hard example determination for the negative collection and positive pair. For the negative collection, indistinguishable data points in embedding space become apparent in the data distribution, as depicted in the negative sampling view. Since data points are mapped to their positive pairs in a man-to-many fashion, the non-parallel connections in the bipartite positive sampling view reveal their difference. Furthermore, measuring the distance between the data points and their positive and negative samples provides a straightforward way to access the training status. Therefore, we visualize the mean and variance of this distance in the comparison view. These visualizations accurately reflect a typical case of local minimum named model collapse, which we will illustrate in an upcoming usage scenario.
This usage scenario illustrates how the experts can clearly understand the training stage, easily steer the contrastive framework, and induce their domain knowledge into the trained model in the context of data missing with our proposed CI-VIS system. Firstly, the expert chooses the dataset and CNN model into the system. Then, he inspects the overall data missing rates in data info. To avoid data missing, he ticks 46 features according to his domain knowledge, without the features with missing rate larger than 0. Following the guidance view, the expert moves to the updated negative sampling view. The narrow distribution of green circles and the far distance between the green and red circles imply that current distribution of embeddings is against the principle of alignment and uniformity. Then he wants to refine the distribution by adding samples into the negative collection. Therefore, he lassos all the semi-data, ticks the hard sampling strategy, drags the rate slider to 0.6 and clicks apply to automatically add 60% of the selected samples into the negative collection, and he clicks the set negative to confirm his selection. In addition, the positive sampling view displays the mapping between the semi-data and their corresponding positive bins, which the expert is satisfied with the default result, so he clicks the set positive to confirm this mapping. After specifying the positive and negative samples, the expert sets the temperature parameter to 0.07, as recommended in the previous paper, MOCO. The model is then trained for short epochs of 100. However, the distance variation to the negative collections, var negative, rapidly decreases to 0, while the mean distances to both the positive pair and negative collections, mean positive, mean negative, quickly increase to 1. These observations suggest that the model collapse occurs. These observations also indicate an overheated training stage. To fix this issue, the expert switches to the initialized model and then adjusts the temperature to 1. In subsequent training using this setting, the expert observes that the mean distances evolve gradually and the training restores to a normal state. After that, the training goes with only semi-data added in the negative collection. As a result, the decreased mean negative, 1 to 0.94, the increased mean positive, 0 to 0.97, and the wider distribution of green dots pose an evidence that the semi-data are pushed apart, as the expert wishes. The above results with the semi-data in the negative collection should be intuitively compared to the case where full data is added into the negative collection. He follows a similar series of operations with above, except that he additionally lassos the full data with a sampling rate of 90% to add 470 samples into the negative collection. Therefore, it is a comparative study to inspect the influence of adding semi-data and full data into the negative collection. After another round of training, the expert observes that in mean positive, the second result is below the first result, but in mean negative, the second result goes from the bottom up, but is also below the first result. In the circle glyph of the comparison view, the distribution of the full data range is wider compared to the first result, which also aligns with expert's expectation. For the second result, the full data are both within the negative collection and the positive mapping. The model must find a balance. Therefore, the second var negative converges slower, the embeddings of the full data go closer, which means both mean negative and mean positive increase during the training stage, but reach a lower level compared to the first result. After the training stage, the expert has enough confidence in the trained model, with which he clicks Infer to apply inference. He then validates the prediction by their inference. Clicking a row, its activation is shown below. The highest activation often lies on the GR-live area, meaning the ground living area in square feet, which is important to house price prediction.
To evaluate the effectiveness of a system, we conduct quantitatively and qualitatively experiments. In quantitative experiments, we compare series with classic data computation algorithm for two tasks involving two models. Our method excels in the regression task and shows comparable performance in the classification case. In the quantitative user study, participants are asked to experience our system and offer assessments. Two results are impressive. The high scores in informativeness and decision-making prove that our system succeeds in the direct control of embedding distribution. And two highest average ratings are given to questions Q10 and Q2, which are about the training transparency of CL model. To summarize, this study presents a framework based on CL that is capable of modeling observed data with missing values in the ML pipeline. Our proposed framework utilizes both complete and incomplete data without any form of imputation. In addition, we introduced a visual analytics system called series, which integrates the CL-based framework to assist experts in leveraging their domain knowledge and engaging in co-adaptive decision-making. Our work not only proposes a different path to resolving modeling observed data with missing values, but also a broader adoption and deeper understanding of contrastive learning.